Testing, testing. Yes, mic is working. Hello, hello, hello. Good morning and good. I really should just start saying hello world, which saves me from whatever time of day it is. We made it, and I am technically early, so pat on the back for me. Yeah, I was. Oh, forgot to do the soft murmur thing. Okay. I was actually like woke up extra early just to edit a video that I wanna hopefully post. Maybe like it's Thursday. Maybe early next week. I think that would be possible. And the video is nothing coding related, so sorry about that. It's just the highlight of the Duolingo stream that I did. I think that would be fun because, yeah, like I said, I actually enjoy watching people do Duolingo. I don't know why. It feels weird. Alright, so what is wrong with the title of this? Why is the title of this course wrong right now? That makes no sense. Sorry. If I refresh, would it update? Because the title was wrong? Okay, now the title is correct. Apologies. I don't know why I was using the old title. Okay. So, let's do the learning thing that we're here to do. Which is this. By the way, I actually will take input of my 안녕하세요. Hi. Question is the wing. Should it be this wing or should I change it? I don't think it's too big, but my question is there are cooler wings and I wasn't sure if it should be this wing or another wing. Should I show you the other wing that I was not sure if I should select or not? Wings. The other wing that I was not sure if I should select because I thought it might look like this one looks like a statement, but the other one doesn't. Oh, see, you can't even see it. Ha. Because where's my mouse? There's my mouse. What? It blended. Is it green? I thought it was gray. It blended with the background. Why did I? Whoa. It really is gray, not green. And the other dark wing is this one, which I love, but I thought it doesn't match this situation. It's the cutest thing. It's mechanical. Yeah, it's too much. It's too much. There we go. Today is a wingy day. That was that. I don't think that was interesting. I have the background noise on. Let me know if I should turn it. Like just make it different. I don't know. Should we have thunder and then once in a while a crack of the thunder? Okay, so let's start with today's lesson. I should stop getting distracted. I don't think I need this to be here. Not anymore. Thank you. So, what we did last time, which was yesterday, was an introduction to the HuggingFace dataset library and working with datasets that are not from HuggingFace library. So either they're on your computer, like local, or they are remote. And then now, today we will be, I'm guessing we'll be working with data, slicing and dicing. So that will be on the HuggingFace side. On the Carnegie Mellon University side, still sequence modeling, and yeah, I think I'll start with HuggingFace. It will be more engaging, most likely. So yep, I always bring something to drink. The rain sound is so nice. So grab a coffee or a tea or whatever you like, and let's do this. I love the background noise. And if it's bothering anyone, please let me know. So most of the time, the data you work, why isn't it selecting? Yes, it is. Okay. Actually, my hand hurts because I was hit a bit, I wouldn't say badly, but I was hit unconventionally. Like, you wouldn't expect this type of kick in the arm, and when I lift my fingers it hurts because I do taekwondo. Not because I was doing street fight or anything. Not yet, anyway. I need to be like at least red belt before I go to the street and fight people. I'm kidding. Okay. Yeah, the data you work with won't be perfectly prepared for this. For training models, in this section we'll explore the various features of the HuggingFace dataset that HuggingFace datasets provide to clean up our dataset. Okay, so features that are from HuggingFace and not pure Python. Let's see.
How to slice and dice a dataset. Most of the time, the data you work with won't be perfectly prepared for training models. In this video, we'll explore various features that the datasets library provides to clean up your data. The datasets library provides several built-in methods that allow you to wrangle your data in various ways. In this video, we'll see how you can shuffle and split your data, select the rows you're interested in, tweak the columns, and apply processing functions with the map method. Let's start with shuffling.
So, wrangling the data, shuffle and split, select and filter. You mean like... Okay. Is there a better word for filter? Rename, remove and flatten, map.
And apply processing functions with the map method. Let's start with shuffling. It is generally a good idea to apply shuffling to your training set so that your model doesn't learn any artificial ordering in the data. If you want to shuffle the whole data set, you can apply the appropriately named shuffle method. You can see an example of this method in action here, where we've downloaded the training split of the squad dataset and shuffled all the rows randomly. Another way to shuffle the data is to create random train.
So we have shuffled. Squad is the name of our data. I was like, why is it named squad? You just say dot shuffle. I love the seed 666. Is that why?
This method in action here, where we've downloaded the training split of the squad dataset and shuffled all the rows randomly. Another way to shuffle the data is to create random train and test splits. This can be useful if you have to create your own test splits from raw data. To do this, you just apply the train test split method and specify how large the test split should be. In this example, we specify that the test set should be 10% of the total dataset size. You can see that the output of the train test split method is a dataset dict object whose keys correspond to the new splits. Now that we know how to shuffle the dataset, let's take a look at returning the rows we're interested in. The most common way to do this is with the select method.
Okay.
This method expects a list or a generator of the dataset's indices and will then return a new dataset object containing
Only indices? That's weird. And why is it 0, 10, 20? 40 and 80. How are these indexes? Are there 80? Okay.
Getting just those rows.
Rows? Who selects from rows? I thought it's like an SQL select. Ooh. This feels weird. Is it just me?
If you want to create a random sample of rows, you can do this by chaining the shuffle and select methods together. In this example, we've created a sample of 5 elements from the squad dataset. The last way to pick out specific rows in a dataset is by applying the filter method.
Okay, see, filter and row makes sense because you're filtering the data, but select is for features for the columns. I'm really passionate about this.
This method checks whether each row fulfills some condition or not.
Double checking if the rain sound is loud because it feels loud for me.
For example, here we've created a small lambda function that checks whether the title starts with the letter L. Once we apply this function with the filter method, we get a subset of the data just containing these rows. So far we've been talking about the rows of a dataset, but what about the columns? The datasets library has 2 main methods for transforming columns: a rename column method to change the name of the column, and a remove columns method to delete them. You can see examples of both these methods here.
Rename columns, remove columns. Yes, one here, one there. Okay.
Yeah. Some datasets have nested columns, and you can expand these by applying the flatten method. For example, in the squad dataset, the answers column contains a text and answer start field.
Okay.
If we want to promote them to their own separate columns, we can apply flatten as shown here.
Why did my brain think flatten is putting them together instead of okay, all right.
Now, of course, no discussion of the datasets library would be complete without mentioning the famous map method. This method applies a...
I actually love the map method. Hi, coffee. It was and hi. What was? Rain? Loud or nice? Because I think it's nice. Or are you agreeing with me with the filter and the select? Because I don't know.
custom processing function to each row in the dataset. For example, here we first define a lowercase title function that simply lowercases the text in the title column. And then we feed that function to the map method, and voila, we now have lowercase titles.
Oh, we can do that? Really? That's really interesting. You say, oh, this way is like you give it this is weird. I don't know why. I find this to be weird. But in a good way? Title. So we're working with the metadata. Okay. Rain. Good or loud? Yeah. Because I really love it. I like it.
The map method can also be used to feed batches of rows to the processing function. This is especially useful for tokenization, where the tokenizers are backed by the tokenizers library, and they can use fast multi-threading to process batches in parallel.
We can do batch. Okay. I remember that as well. Thank you. I think maybe the select is like select where. Yeah, fair. But I am not happy with it because select allows you to select columns, where allows you to filter. We know that. I'm too angry about it. So, slicing and dicing our data. Similar to pandas. So you're okay. HuggingFace datasets provide several functions to manipulate the content of dataset and dataset dictionary objects. We already encountered the dataset.map method in chapter 3. We loved it. Hi JSS, hey! Did I hit the mic while waving? Why am I waving? Who can see me wave? Anyway, hi. Welcome. Yep. Chapter 3, yes. We saw the map in chapter 3. We used it. And in this section, we'll explore some of other functions at our disposal. Okay. By the way, we just started, so we're seeing what kind of data wrangling is being done on HuggingFace. For this example, we'll use the drug review data set. So they don't use pandas at all. I have an inkling that basically they just made a front for it. Like, I think the HuggingFace stuff is just a prettier version of what's already out there, and they make a front, an interface, right? Maybe like it's really similar. Let's see. If you're like used to pandas, let me know if you think they are similar or not, because I have barely worked with pandas. So we are using drug review data set hosted on the place where I couldn't access the data set. We'll learn how to access the data set. Data set not found. That's funny. I'm gonna search for it. Drug review. There are 2 versions. Abstracted, probably. Yeah, that's what I'm guessing. There are 2 versions. Version 1. Oh, okay. There. This is the smaller one. Drug. Okay. Let's see. Hosted on UC Irvine machine learning repository, which contains patients' reviews on various drugs, along with the condition being 10 star. This is the 10 star. I think we'll be doing this one. Rating on the patient satisfactions. Okay. I didn't think drugs were given 10 star ratings. First, we need to download and extract the data, So someone told me yesterday to do the wget, and I didn't, and now I realize my mistake, and I would like to humbly apologize. Please forgive me. Okay. Wget and unzip. Okay. My fault. Absolutely my fault. Should I continue with this? I think I want to continue with this. Chapter, what chapter are we in? 5? 5. So let's just call it chapter 5 and try to run as much code here as possible. HuggingFace chapter 5. And here, let's add a text line that says slice and dice. And then the code line. And is that the correct link? In case it's not. By the way, I think somebody was coffee. Like, I think that I made myself clear. Is the link? No, the link is different. Let's think that we're getting no error. I thought there would be an error because the link they were using was an error. Good. Alright. So we have drugs.com raw data set from wget, and is it unzipped in our file? No. Wait, didn't we download it? It's not in the list of... Is that a refresh button? Yes. Aha, here it is. We have a tab separated, by the way. Let's look at the test. Can you see it? It's behind me. It's loading. Okay, while you do that, since tab separated is just a variant of comma separated, obviously, that uses tabs instead of commas as separator, we can load these files by using comma separated value and specifying that the delimiter is a tab. Yep. That was also discussed yesterday. We're putting them together, and then we're saying delimiter is tab. And yeah, good. Oh, this is what it looks like. Let's see. We have drug name, condition. What did I do? What did I do? I just clicked it. Just ran away from me. One more time. This is going to take a while. Okay. Drug name, condition, review, and date, and useful count. What can we see? Okay. Date, useful count. Is that the review? 10 out of 10. Would take it again. 2 out of 10. 9 out of 10. Okay. Fun. Fun. Do I know any of those names? I doubt it. Okay. So we have our downloaded dataset, and for some reason yesterday I thought downloading would mean putting it on my computer, and I was like, I would never. Now I realize that you can download it into Colab. Oh, do I need to run? And then we put the training and testing together. Why? So that we do the tokenization and stuff. A good practice when doing any sort of data analysis is to grab a small random sample to get a quick feel for the type of data you're working with. In the HuggingFace datasets, we can create a random sample by chaining the dataset .shuffle and dataset .select functions together. Okay. I think there should be a select columns sort of thing. Because error. Why? Failed. Error with tokenizing string row. Are the names different? Drugs, test raw. That line ran, right? Oops. Not your fault. Should I try and do... one, just to see if it works? Train only. Train only works. And it's a panda zero, I think, so confirmed rad by HuggingFace. Yeah. We figured them out. What's the issue with this data files? Because just calling it works fine. Let's do test only as well. While we're at it. We did train only, no problem. Is the issue with you? No. Together? Ha! Schrodinger's code. When you run it without looking at it, it doesn't work, but when you run it while looking at it, it works. Okay. So we say drug dataset train part. Shuffle me 42 seeds. And then select me a range of 1,000. Let's see if my hand can write this code. So we're taking a sample. Got it. Calling it drug sample is weird. I know what changed exactly. Me looking at it. Drug sample. The other day, like during, was it Duhu or was it Yuke's chat? We were just calling coding wizardry, so now it feels like it. Where were we? We are getting you drug data set, the training part, dot shuffle seed. Is that how it works, or was it 42 and select. Did it say random range? I thought it said random. 1,000 is too much. Let's just go 100. Wrong one. Range. If we're just doing this as a sample, I've heard it's called Heisenberg. Wait, I don't know why. Should I know something about Heisenberg? What do I know about Heisenberg? I have no idea. Oh, I searched for Heisenberg. What? It's real? I thought you were joking. Disappear or alter its behavior when one attempts to study it. Astaghfirullah, subhanallah. What is this? Yeah. This is crazy. Thank you for teaching me what a Heisenberg is. So it was not Schrodinger's bug. I know, learned new jargon. This is what we're here for. Heisenberg. We are here to learn things that are not useful, I think, maybe. Let's peek at a few samples. Examples of the sample. By doing that, we say drug sample, and then we say give me 5. Go. That's a lot. How is this 5? It's just 1. Are we saying 5? There's few samples. Isn't it just 1? Oh well. We have condition, acute. What's used for? Whoa, these are weird stuff. Like, different stuff. The term is of fun on the name of Heisenberg. I've heard Heisenberg, I just don't know. The physicist who first asserted the observer effect of quantum mechanics, which states that the act of observing the system inevitably alters its state. Yes. Yes. I can piece these things together because I've watched enough Veritasium videos, I think. I thought cat in a box. Why wouldn't they call it? I guess Schrödinger is too famous, so Heisenberg should. I mean, I'm guessing he's also very famous. Thunder. Note that we've fixed that seed in dataset.shuffle for reproducibility purposes. Dataset select expect an iterable of indices. So we've passed a range of 1,000. I did 100 because I'm lazy. To grab the first 1,000 example from the shuffle dataset, from this sample, we can already see few quirks. I don't see any quirks. What? How am I supposed to see quirks? Unnamed 0. I didn't have unnamed. Oh, I did. Wait, what is that? I didn't notice it. Wait, when we're saying look at samples, these are rows or columns? I don't get it. Because is unnamed supposed to be a name of a feature? Because that's what I feel like it is. The cat was in the box because I heard him scratching. Why redacted? What happened? What are we redacting? A cat won't stay in a box. Unnamed 0. It's a column. Okay. Looks suspiciously like an anonymized ID for each patient. Okay. The condition column includes a mix of uppercase and lowercase labels. Yeah. This one starts with out uppercase. Reviews are of varying lengths. I noticed that the review looks ugly. It's probably HTML. Mix of Python line separators as well as HTML character codes. I think it's like from editor thing. We don't talk about what happened to patients. Redacted. Wait, there's a redacted? Or are we talking about the cat? Because we're looking at code, and I was like, a drug related stuff, and I was like, is there a patient here? Let's see how we can use datasets to deal with each of these issues. To test the patient ID hypothesis for the unnamed 0 column, we can use the dataset unique to look at a list of okay, I like that. To verify the number of IDs match the number of rows in each split. Oh, we're just checking. Okay. For drug dataset keys, so we're just looping. Assert length of the split as in training or testing, equals the length of that dataset split dot unique of this unnamed patient. We're guessing. Okay, because it's a rating thing, the cat can be a patient then. Of course they can be. I think they mean like patient 0 with column ID being called unnamed. Patient, it's a column, yeah. Wait. I got no output. It just ran. Shouldn't I get a true or false? Or because it's a split for loop? What does assert mean? I have no idea what assert is supposed to mean in this context. Used for debugging? Where does it go? True. Hold up. If condition true, nothing happens. Oh, I didn't know that. Okay. So the fact that nothing happened is true. This seems to confirm our hypothesis, so let's clean up the dataset by renaming the unnamed column to something more interpretable. We can use dataset dictionary.rename column to rename it. Okay, so we have to say our dataset, new line of code, equals udataset dot rename column, and then give it names. Assert for test. I didn't know that. I hadn't used it before. Original column name, new column name. Before I do that, let's look at it first. And then when I run it, let's look at it again. Oh, I should have. Yeah. What? Did I forget any? Original is not in the dataset? Because I just renamed it. I renamed it twice. My bad. Just hide. I ran this line twice, so it doesn't exist anymore. Unnamed became patient ID for both splits. Okay. Use unique to find number of unique drugs. And conditions in training, and I mean, I can just like call this and look. Do I need to do a for loop? I don't think I do. Like I can say dataset train and then dot unique. How does one write the word unique? Oh, hi, thank you. We want to check for how many drug names there are in this dataset. Oh. Sorry. Why did I do that? That's the correct way. Oh, it's not a count. Can I do len? Does that work? Yeah. Maybe many languages I think let you assert in like C. Might be function call or macro. I've seen it. I haven't used it. So, yeah. 3,400 drugs. Wait, I thought it was like a lot more instances. Fair. But, yeah. Let's normalize all the condition labels using dataset.map as we did with tokenization in chapter 3. We can define a simple function that can be applied across all rows of each split in drug dataset. Okay, I'm back. I keep needing to yawn. Sorry. So, did I sleep too little last night? Something tells me I didn't sleep enough. Less than 6 hours. Great. So, by normalizing, we are making them, for now, all be lowercase because we had an issue with the condition having different cases. And that makes it not match when we're doing unique, right? Test frameworks use a ton of asserts. Okay, something tells me I was bad at testing stuff. So to make them lowercase, I really love this idea of having a function and then applying the function on the data set. That felt new to me. Is that supposed to be the error? Attribute error? Oh no, we've run into a problem with our map function. Does that have to do with batching? I don't think so. From there we can infer lower doesn't exist for column, that some of the entries in the condition column are none. Oh, I didn't read this. Oh, none. More coffee. Okay, sure. Let's do coffee. I mean, we have one coffee in the chat, so I'll be good. Yeah. I do enjoy drinking coffee and making coffee in the morning. We can infer that some of the entries in the condition are none, so we'll have to update none. Or, oh, that's really loud. I'm sorry. I think that was a motorcycle, right? Tried to mute, but I didn't catch it early. Cannot be, as they're not strings. So let's drop these rows using filter, which works in a similar way to map and expects a function that receives a single example of the dataset. Instead of writing an explicit function like this, we're just going to write. You're teaching me about lambda. Okay. Are we laughing about the motorcycle, or are we laughing about the fact that I yawned twice in 5 minutes? Instead of writing it like this, we're running the filter and then running it like this. We can do it using one line, using the lambda function. In Python, it's almost motorcycle. Okay, motorcycle, haha. It's almost midnight. Okay. Start your like sleep routine if you have one, and then you can go to the website I'm listening to and just listen yourself, and then hopefully you fall asleep and have a nice sleep. Lambda functions are small functions that you can define without explicitly naming them. They take the general form lambda argument expression, where lambda is one of Python's special keyword. The word lambda. Okay. Argument is a list / set of comma separated values that define the input to the function. Expression is the operation we want to execute. For example, we can define a simple lambda function that squares a number as follows. Okay, but we'd have to use it. To apply it to an input, we need to wrap it and the input in parentheses. Lambda input. Cool. Can't finish early your other work. You have other work to do? Okay. I like how they made very accessible of all experiences, right? Just pausing the code, explaining something for you, and then continuing. I also really appreciate that. I've never been comfortable to write my own lambda, I think. Like one line statements, if conditions are okay, but is that lambda? I don't know. Similarly, we can define lambda functions with multiple arguments by separating them with comma. For example, that's fancy. Look at that. We have a base height, and then this is how you give it the base height. Lambda functions are handy when you want to define small single-use functions. Yes, they are single-use. For more information about them, we recommend reading the excellent Real Python tutorial by Andre Bougard. Let's Lambda calculus, Real Python. Whoa, that's a... No way. It was 30s? Pretty. I'm gonna go back. In the HuggingFace datasets context, we can use lambda functions to define a simple map and filter operation. So let's use this trick to eliminate the non-entries in our data set. So the idea for us was saying dataset column name is not none as a filter, right? To do that, we're saying filter, naming lambda, saying this is, I'm guessing, the like return output, and then this is what we want to do with it, and it works. Should we write our own lambda ourselves? Wait, what was the error here? Ah, the none thing. So before we do this, we're supposed to say drug test equals drug test dot filter, and then the lambda function. Is that how I'm supposed to do that? Okay. And then we say lambda for x condition is not none. Oh, lambda is getting an error. Why? It's just supposed to be... Oh, there's a B? Lambda. Sorry. I didn't see the B, I swear. Ooh, that took 3 seconds. It worked! With the non-entries removed, we can normalize. But x is the parameter name, the lambda. Your lambda is also misspelled. We'll take as an input. Okay. It's like the thing that's in here. Like that parameter. Okay. By the way, I'm pointing out your spelling mistake because I made a spelling mistake, and I want to know that we're all human, and we make spelling mistakes. With the none, yes, okay. What do we do now? Just take a look at how it is. Let's take a look. Number of rows. We filtered the rows, right? So number of rows should be different. Oh, definitely different. We lost 1,000 up here, and down here we lost from 700 to 400. We lost a couple hundred here as well. Let's look at... Oh, hi! Oh, okay. I'm guessing that was YouTube. I still don't know how I get those notifications. Yep, that was from YouTube. Thanks for the subscribe. Thank you. Thank you for joining us, and for the subscribing, and for the other stuff. Like, just being here with me is enough. Which you don't have to be. Wait, didn't we just apply lower condition? What happened? Why is mine not lower? Oh, what? Map doesn't work like map equals map. Did I not run this code? Huh? condition. I don't get it. And why are there... What happened? What did I do wrong? I'm stuck. We filtered by none. We said dot lower. Can we do lambda here as well? Because now I'm mad. But I don't think it works that way because of the column name. Like, should I run this first? Oh, you know what? I'll rename it. Lowercase con. Run new. And then add this map B. Okay. Are we getting another Heisenberg? Your function argument. We have example. Okay, this is taking longer. I'm hoping that's a good thing. Did it not like the fact that the mapping was inside with the definition of the function? Taking longer. Okay, bismillah, let's do this. Nope, didn't work. Fun. Let's do upper. Like, it's just not applying. Condition is there, so it shouldn't be you. I don't get it. I'm not doing anything special. Let's double check the code. Or better yet, I will run their collab, and if theirs applies and mine doesn't, I'll just, I don't know, should we rage quit or something? Let's say I'll just run everything that's there. Let's do a run before. It's fine. Upper didn't work as well. Yeah? Did it? Oh, we didn't run this. Upper didn't work as well. Fun. Okay. So you do that. I'll wait for this to run. And be angry in the meantime. It didn't work. Now that we've cleaned up the labels, let's take a look at cleaning up the reviews because of all the HTML stuff. Creating new columns. Whenever you're dealing with customer reviews, it's a good practice is to check the number of words in each review. A review might be just a single word like great, or a full-blown essay with thousands of words, and depending on the use case, you'll need to handle these extremes differently. To compute the number of words in each review, we'll use, oh, I have an error because it's the error of the none thing. And then we can run you. Oh, what did I do? The filter. And then you. Swear to God, if yours works and mine doesn't. I have the lambda function up here as well. has a different function. Let's see. Okay. Where was I? To compute the number of the words in each review, we'll use a rough heuristic based on splitting each word by white space. We can't use unique. Okay. Let's define a simple function that counts the number of words in each review. We can't... Oh, I was like, can we just do len? We are just doing len. It worked for you? Of course, wait. Of course it did. Of course it did. Of course it would. Alright, I'll start over. From the thing that was here, I'll just copy and paste whatever you gave me. Because apparently that's supposed to work, not my code. This is supposed to be... I mean, now I don't have... Where are we? The condition... This time it should work because I already did the no more none thing. Should I look at your no more none lambda? Because I swear they are... I don't have to swear, but I am. I don't know why. Are they not the same? Did I make a mistake? If they're not the same... Look, literally the same. Okay. And then, after that, apparently this was defined before it, which should not matter. It doesn't matter. There. Run. Like the wind. And then here, we have this. Am I calling something different? Drug dataset. There. Ooh. Wait, am I calling it in a different way? I don't get it. It worked. I copied the function. Should we try upper, just in case? Upper. Oh! The map! I forgot to say equals itself. Okay, now I get it. My fault. I should apologize to HuggingFace people. Why did I think I didn't need to do the map like that? Where did you give me that idea? Where did I give myself that idea? Did I not copy and paste? Apparently I didn't. See? Here. I copied and pasted from here. Okay. And then I didn't look at that line better. But I mean, we're learning. Yay, upper works as well. Let's go back to lower. Making silly mistakes where you hold your ground with the silly mistake is fun. There. Next, we are supposed to create count the length. We are adding a new column that's the review length. Okay, let's write the code by hand and be angry when it doesn't work, because then I learn more that way. We are calling this review counter, and we should get the database, right? Dataset. Sorry for calling you database. I'm sure you're mad at that. Dataset. And then return what we're calling it review length, and then we're saying data set no split, right? We're saying len of the dataset.unique, but are we not looking at a split? Unique of a column. That's not how I write it, right? Oh, split? Oh, split by space. We all missed it too. Thank you. Thank you for making me feel better. I get heated up a bit too quickly. Dataset review dot split, which means split by space. We're not telling it what to split by, so we're just looking at how many words there are that are separated by space. Don't have to be words, can be funny HTML stuff. What do we do after that? We do another map and then look at it. Let me do the mapping myself so that I make the same mistake again. I'm just gonna copy and paste and give you review counter, and then I guess look at a few again. No, wait, that's not what we did. Can I look at it this way without telling you which column I want to see? Or is that... yeah, seems like it. Go. For you, this review length is 17. It has no side effects. Cool. Let's see if I can see what's there. Good night. We'll review you don't... cool. If you review it tomorrow and have any notes, let me know, whether it's as a comment or wherever. But you don't have to. You can just come back to the code and check it yourself. Wish you sleep dreams. Yeah, have a nice night. And thanks for stopping by. Okay, no matter how many I say, it just gives me one, which is fine. Oh no, it's not. It's giving me 1, 2, 3, 1, 2, 3, and review 1, review 2. Review 1 is review 1, review 2, review 3. Got it. Which are 17, 141, 134. Cool. How much longer in the slicing and dicing? Much more. Definitely more. I'm actually really happy, but okay, let's see. Ooh, that's a lot. Let's see how long that takes us. Thank you too. Thank you. Okay. So as expected, we can see it has been added to our training set. We can sort this new column with sort. Should we sort it? See what extreme values look like. Can I sort it the other way around? Because extreme values are excellent. Useless. That's a good one. Useless. And then, okay. Meh. For pain. Oh, now I feel bad. They had written, okay, for pain. What was that? Hold up. Rating 6. Oh. As we suspected, some reviews contain just a single word, which, although it may be okay for sentiment analysis, would not be informative if we want to predict the condition. Yeah. Why do we want to predict the condition? We can That's okay. All right. Sort. We just sorted by column name. An alternative way to add a new column to the data set is with add column function. I remember that one. This allows you to provide a column as a Python list or NumPy array and can be handy in situations where map is not well suited for your analysis. Like when adding one, what is it called? Static, like constant value, which I don't know if we should, I don't know. Anyway, I don't know if we should use that for that case. Let's use filter function to remove reviews that contain fewer than 30 words. Similarly, what we did with the condition column, we can filter the very short reviews by requiring that reviews have a length above this threshold. Okay, so we're filtering by lambda. Let's try. Last time we also did some we did the not none filtering. So it's basically that, but this time for review, did we call it review count? Review length should be more than 30. And then we're looking at what? Okay, close that. Yeah, please do. Print num rows. If you actually don't even say num rows, if you just say dataset, it gives you a look as well. Oh, wrong button. Like this, it should work as well. We had 16. Wait, no, is that updated? No, that's the old value. And now we have 13,000. Wait, no, 138,514. Oh, that's a lot. And then now 46,000. Why did my brain read it as 100 last time? As we can see, this has removed around 15% of the reviews from our original training and test sets. Oh, let's do a sort to inspect. Okay. The reviews by largest number of words. I will need to check documentation because I don't know how to write ascending and descending. Sort. Reverse. If true, it becomes descending. Alright. So we say you. Are we doing equals to you again? Because is that what we did last time? No, we're just looking at it. We're looking at the training dot sort, and then reverse equals true. What else? I should give you the name of the thing I want to sort. Got it. It would be like that, right? Because the name of the column that I want, and then saying whether I want it reversed or not. Do I tell you the name of the column as if like column name? Does that work like that? Oh. There's an S, column names. Like, would it be alright if I give it to you? Oh. Column names. Like this. Would that work? Loading. That's taking a while. Is it because of the reverse equals true? The last thing we need to deal with is the presence of HTML character codes in our review. We can use Python's HTML module to unescape these characters like so. Oh wow, that's pretty. Didn't know we had such a thing. So we make it a lambda function. All right. So more information about. I think I'm gonna pause on this actually. Yeah. The superpower of the map method. We'll pause here after we. This is taking too long. Is that all right? Is that supposed to happen? I'm just gonna pause you. Don't. Stop. No. I don't want to restart runtime. I've ran too many things. Alright. We can do the unescape later. Yes. We can see map is quite useful for processing data. We haven't even scratched the surface of everything we can do. Let's start scratching surfaces starting tomorrow for HuggingFace. And now it's time to go to class. This is annoying me. This is really annoying me right now. I can't do the unescape. It's okay. We have patience. Let's refresh this. And by the way, small note, just with the monitoring of, you know, here. Should I zoom in a bit? Nope, doesn't work. When I make it full screen, you cannot see the closed caption subtitles. So I make it not full screen so that you can see the captions when he's away from the mic and all that. So yeah, just wanted to let you know that that's why I make it smaller. Even though it sounds counterintuitive, maybe. But I think the captions are necessary. And this is taking its just fine time. Sure, do that. Let's go.
Cool. So the basic modeling paradigm that we use for things like this is extracting features and predicting. So this is exactly...
Added the, I just did this and the rain sound became really loud. Is the rain sound really loud? Should I lower it a bit? Okay, lowered a bit. I still like it, but it felt a bit loud. I hope it's better now. I love the thunder as well.
The same we use for things like this is extracting features and predicting. So this is exactly the same as the bag of words model, right?
Okay.
The bag of words model that I talked about the first time, we extracted features. Based on those features, we made predictions. So it's no different when we do sequence modeling. But
by the way, I hope the rain sound isn't too traumatic for people where it's winter right now. For me, it's probably like, I don't know, 30 something outside, so the rain sound is calming.
As we made predictions. So it's no different when we do sequence modeling, but the methods that we use for feature extraction is different. So given an input text X, we extract features H and predict labels Y. And for something like text classification,
Given an input, we extract features and predict labels. That sounds fair. I think comes and goes. I thought you turned it down at the start of the stream, but in hindsight, I think the room just went quieter. I think so. I think so. Like, does it make any changes? Oh yeah, it does. It absolutely does. When I change, let me bring it here. I make changes from here. And it does make changes. Here, it matters what you know, do with it, but this is like how loud you want it to be. It's a really useful and simple website. A soft murmur. Love the name as well. Okay. Yeah, do let me know if you want like different effects, because it would be fun. Like if you want less rain and more crackling, let me know. If you want the bowl sound, sure, we can have a yoga session.
what we do, and for something like text classification, what we do is we, so for example, we have text classification or sequence labeling. And for text classification, usually what we would do is we would have a feature extractor. From this feature extractor, we take the sequence and we convert it into a single vector. And then based on this vector, we make a prediction. So that's what we do for classification. For sequence labeling, normally what we do is we extract one vector for each thing that we would like to predict about. So here, that might be one vector for each word. And then based on this, we would predict something for each word. So this is an example of part of speech tagging, but there's a lot of other sequence labeling tasks also.
Okay.
And what tasks exist for something like sequence labeling? So sequence labeling is a pretty big subset of NLP tasks. You can express a lot of things as sequence labeling. And basically, given an input text X, we predict an output label sequence Y of equal length. So
Equal length? Y of equal length? What does that mean?
So this can be used for things like part of speech tagging to get the parts of speech of each word. It can also be used for something like lemmatization. And lemmatization, basically what that is it is predicting the base
Root?
form of each word.
Base.
And this can be used for normalization if you want to find, like, for example, all instances of a particular verb being used or all instances of a particular noun being used. This is a little bit different than something like stemming. So stemming, normally what the stemming would do is it would chop off the plural here. It would chop off S, but it wouldn't be able to do things like normalize saw into C because stemming just removes suffixes. It doesn't do any sort of normalization. So that's the difference between.
Stemming removes suffixes, prefixes, and stuff. Lemmatization takes you back to the base verb and stuff. Good to know.
Lemmatization and stemming. There's also something called morphological tagging. In morphological tagging, basically what this is doing is this is a more advanced version of part of speech tagging that predicts things like, okay, this is a past tense verb, this is a plural, this is a particular verb form, and you have multiple tags here. This is less interesting in English because English is kind of a boring language morphologically. It doesn't have a lot of conjugation and other stuff, but it's a lot more interesting in more complex languages like Japanese or Hindi or other things like that. Chinese is even more boring than English, so if you're interested in Chinese, then you don't need to worry about that.
Huh.
Cool. But actually, what's maybe more widely used from the sequence labeling perspective is span labeling. And here you want to predict spans in labels. And this could be named entity recognition. So if you say Graham Neubig.
Spans. I didn't know what he meant by that, but the rain is picking up again. But yeah. Named entity recognition. I know what that is. Okay.
Neubig is teaching at Carnegie Mellon University, you would want to identify each entity as being like a person, organization, place, governmental entity, other stuff like that. There's also things like syntactic chunking, where you want to find all noun phrases and verb phrases. Also semantic role labeling, where semantic role labeling is demonstrating who did what to whom. So it's saying this is the actor, the person who did the thing, this is the thing that is being done, and this is the place where it's being done. So this can be useful if you want to do any sort of analysis about who does what to whom, other things like that.
If it's a whodunit or wait, how many are there? There's a whodunit. Oh, I forgot. Anyway.
There's also a more complicated thing called entity linking, which isn't really a span linking task, but it's basically named entity recognition, and you link it to like a database like Wikidata or Wikipedia or something like this. And this doesn't seem very glamorous, perhaps. You know, a lot of people might not sound like be immediately excited by entity linking, but actually it's super, super important for things like news aggregation and other stuff like that. Find all the news articles about.
Am I supposed to be immediately excited when I see the use cases? I'm so excited about named entity recognition. You know what? It is cool when you first learn about it. I'll give you that.
Super, super important for things like news aggregation and other stuff like that. Find all the news articles about this celebrity or something like this. Find all of the mentions of our product, our company's product. And
I remember learning about Facebook's graph thing, similar stuff. But no, you're talking about one thing. Linking things of like one celebrity, one entity, one product. Okay.
Social media or things. So it's actually a really widely used technology. And then finally, span labeling can also be treated as sequence labeling. And the way we normally do this is we use something called BIO tags. And here you predict the beginning, in, and out tags for each word or span. So if we have this example of spans, we just convert this into tags, where you say begin person, in person. O means it's not an entity, begin organization, in organization. And then you can convert that back into.
Doesn't the person end? Out tag, begin tag. We have the organization beginning, but not the person ending.
Into these spans. So this makes it relatively easy to kind of do the span prediction. Cool. So now you know what to do.
Span is supposed to be like a range, right?
If you want to predict entities or other things like that. And there's a lot of models on like HuggingFace, for example, that allow you to do these things. Are there any questions before I move on?
I'm good.
Okay, cool. I'll just go forward then. So now I'm going to talk about how we actually model these in machine learning models. And there's three major types of sequence models. There are other types of sequence models, but I'd say the great majority of work uses one of these three different types. And the first one is recurrence. What recurrence does is it conditions on representations on an encoding of the history. And so the way this works is essentially you have your input vectors like this. Usually word embeddings or embeddings from the previous layer of the model. And you have a recurrent neural network. And the recurrent neural network at the very beginning might only take the first vector. But every subsequent step, it takes the input vector and it takes the hidden vector from the previous input.
Okay.
And then you keep on going like this all the way through the sequence. The convolution is a conditioning representation. It's on local context. So you have the inputs like this. And here you're conditioning on the word itself and the surrounding word.
That is so cool. Local context. To be honest, I didn't know what convolution stand for. Like I didn't know what it meant. I know it can be used in sentences to say something is convoluted, but I don't know if those are similar.
On the right or the left.
Mm.
So you would do something
Pretty.
like this. This is a typical convolution where you have this certain one here, and the left one, and the right one. And this would be a size 3 convolution. You could also have a size 5 convolution, 7, 9, you know.
What? For all, I would like to apologize. I just did a surprise face and the character looked like it had her tongue out. I didn't do that on purpose. But, I was just saying that because it's multidimensional, that's why we can have more.
Whatever else, that would take in more surrounding words like this. And then finally, we have attention. And
I would like to note out and appreciate the animation added and number of slides because you can see it changing at the
like
top.
this.
90, 91.
And then finally, we have attention.
Dedication to craft, right?
And attention is conditioned representations on a weighted average of all tokens in the sequence. And so here, we're
All tokens? No.
conditioning on all of the other tokens in the sequence, but the amount that we condition on each of the tokens differs between them. So
Attention is wizardry, basically. Maybe in a few, maybe after the Transformers. No way, I haven't watched it. What does it look like? I've watched it. Maybe after that I will understand it. Hey, error. Did I get an error? Boo. Sorry. Yeah. We'll see. If after this lecture I will no longer think of it as wizardry, but right now I do.
we might get more of this token, less of this token, and other things like that. And I'll go into the mechanisms of each of these. One important thing to think about is the computational complexity of each of these.
Mm-hmm.
And the computational complexity can be expressed as the sequence length. Let's call the sequence length n. And convolution has a convolution window size, so I'll call that W.
Mm-hmm.
So does anyone have an idea of the computational complexity of a recurrent neural network?
Squared?
So how quickly does the computation of a recurrent neural network
Because it's
grow?
two
And
things?
one way you can look at this is figure out the number of arrows that you see here.
And squared?
Yeah, it's linear. So
Oh,
it's
linear.
basically O of n.
No way.
What about convolution? Any other ideas? Any ideas about convolution?
I mean, if this is linear, then this better be squared, but I thought number of arrows would matter, as in... Okay. No, I don't know.
Yeah, NW, n times W.
Oh, that's good. N times the number of... Why am I thinking squared? Like, why am I going that far? But this one is like n to the power of m or something.
What about attention? N squared, yeah.
Oh, okay. So attention is the worst and it's n squared. Okay. I feared it was far worse.
So what you can see is for very long sequences,
The growth of complexity over the number of straight lines. Yeah. Yeah. Linear times constant and squared. That's pretty good.
sequences, the asymptotic complexity of running a recurrent neural network is lower. So you can run a recurrent neural network over a sequence of length 20 million or something like that. And as long as you had enough memory, it would take a linear time. But if you do something like attention over a really long sequence, it would be more difficult. There's a lot of caveats here because attention and convolution are easily parallelized, whereas recurrence is not. And I'll talk about that in a second. But
Yeah, okay. I just wanted to say that I didn't know the complexity was so different.
Anyway, it's a good thing to keep in mind.
Hmm.
Cool. So the first sequence model I want to introduce is recurrent neural networks. Sorry. One other thing I want to mention is all of these are still used. It might seem that like if you're very plugged into NLP, it might seem like, well,
Everything is
using
attention. Yeah.
So why do we need to learn about the other ones? But actually, all of these are used, and usually recurrence and convolution are used in combination with attention in some way for particular applications where recurrence or the convolution are useful. So I'll go into details of that later.
Okay.
So let's talk about the first sequence model, recurrent neural networks. So recurrent neural networks.
So we'll start with RNN and then CNN and then transformers as its own lecture. Cool. Let's see how long we will be talking about RNNs. Vanishing gradient, whoa! LSTM, these are all RNN. Okay, so convolution happens in 10 minutes, 12 minutes. We can see the finish line.
They're basically tools to remember information. They were invented in around 1990. And the way they work is a feed-forward neural network looks a bit like this. We have some sort of lookup over the context. We calculate embeddings. We do a transform. We get a hidden state, and we make a prediction. Whereas a recurrent neural network feeds in the previous hidden state. And a very simple Elman-style neural network looks, or I'll contrast the feed-forward neural network.
Wonder why CNNs are much more popular than attention. I wouldn't say so. CNNs were popular before attention. Oh, for vision. Obviously, they are very popular for vision. That's, I guess, they have their own use case. So I guess CNN is more useful for vision while attention is more useful for NLP. They are probably definitely, I don't have enough information about research, but they're definitely used together, like in together, or like saying, I'm sure vision is getting attention as well, but how, I don't know, because I'm not in the vision research thing, but they were there before attention, like 2000, like Feifei Li, Dr. Feifei Li, I'm calling her Feifei Li as if she's my best friend, yeah, was like the face of vision, and that was like, I was a student then, wasn't I? Yeah, when that was happening. Yeah, I think face tracking uses transformers. Is this also using transformers, the one that I'm using? That's very cool. Let's see if it gives us some sort of history, like just the fact that recurrent neural networks are from 1990s.
Network that we already know with an Elman-style neural network, recurrent neural network. So basically, the feed-forward network that we already know does a linear transform over the input, and then it runs it through a nonlinear function. And this could be like a tanh function or a ReLU function or anything like that. In a recurrent neural network, we add multiplication.
I'd like to say that I forgot what ReLU is. I know I studied it in Jeremy Howard's class, but I forgot. Okay, no need to remember yet.
By the previous hidden state. So it looks like this. And so if we look at what processing a sequence looks like, basically what we do is we start out with an initial state. This initial state could be like all zeros, or it could be randomized, or it could be learned, or whatever else. And then based on this, we run it through an RNN function, and then calculate the hidden state, use it to make a prediction. We have the RNN function, make prediction RNN, make prediction RNN, make prediction.
Okay.
So one important thing here is that this RNN is exactly the same function, no matter which position it appears in. And so because of that, we just, no matter how long the sequence becomes, we always have the same number of parameters, which is always like really important for a sequence model. So that's what this looks like here. So how do we train RNNs? Basically, if you remember, we can train neural networks as long as we have a directed acyclic graph that calculates our loss function, and then forward propagation and back propagation will do all the rest to calculate our parameters, and we update the parameters. So the way this works is, let's say we're doing sequence labeling, and each of these predictions is a part of speech. Each of these labels is a true part of speech label. Or sorry, each of these predictions is like a probability over the parts of speech for that sequence. Each of these labels is a true part of speech label. So basically what we do is, from this, we calculate the negative log likelihood of the true part of speech. We get a loss. And so now we have 4 losses here. This is no longer a nice directed acyclic graph that ends in a single loss function, which is kind of what we needed for back propagation, right? So what do? Very simple, we just add them together. We take the sum, and now we have a single loss function, which is the sum of all of the loss functions for each prediction that we made. And that's our total loss, and now we do have a directed acyclic graph where this is the terminal node, and we can do backprop with this.
Can I ask what's an acyclic graph? Something that is all connected. Okay. Known as a forest. No graph cycle. Bipartite. Okay, they come and go. Connected. Possibly disconnected is known as a forest. Tree. It's just all connected? Directed. Okay. No cyclic connection. So if you follow nodes, you won't loop. Okay. Okay. Should not make a cycle. Thank you.
So this is the terminal node, and we can do backprop with this.
Terminal node, okay.
This is true for all sequence models I'm going to talk about today. I'm just illustrating it with recurrent neural networks. Any questions here? Everything good? Okay. Cool. Yeah.
His students are smart. Like Git no. Git no? There's a Git no? Or just as a Git. Sorry, I didn't understand that.
So now we have the loss. It's a well-formed DAG. We can run backprop. So basically what we do is we just run backprop, and our loss goes out back into all of the places. Now parameters are tied across time. So the derivative...
There's something poetic about parameters being tied across time. Okay. It reminded me of the K-drama I was watching that ended. No.
into the parameters are aggregated over all of the time steps. And this has been called backpropagation through time since...
that should be title of a new K-drama.
These were originally invented. So basically what it looks like is, because the parameters for this RNN function are shared, they'll essentially be updated.
I mean, it works like Git, which uses... okay. Yes. Git doesn't loop back. And like I can see the arrows, because we were using it inside Visual Studio. So I remember seeing the arrows. Yeah. Cool. Thank you.
They'll only be updated once, but they're updated...
I saw DAG somewhere, but I don't know what it stands for, but I understand how you're trying to explain it to me. Thank you.
From like 4 different positions in this network, essentially. Yeah, and this is the same for all sequence models that I'm going to talk about today. Another variety of models that people use are bidirectional RNNs, and these are used when you want to, do something like sequence labeling. And so you just run 2 RNNs. You run one from the beginning, one from the end, and concatenate them together like this. Make predictions.
Let's look at the arrows. We have first one, RNN, and then this goes here. There's another one, and it goes back. Oh god, too many arrows, too many arrows. How is this being fed into that? It's not. It's just forward. This with this with that, this here, and then this and that here, concatenated, prediction, and then the loss goes back somehow. Oh. Directed acyclic graph. The lecturer also used. Oh! Okay, that's what it stands for. Directed acyclic graph on the previous slide. Thank you. I hope it doesn't bother you when I ask these questions, because I know I can Google it. Am I trying to engage chat? I don't know. I don't think I have a hidden agenda, but I don't know.
Cool. And any questions? Yeah. Does this change the complexity? It doesn't change the asymptotic complexity because you're multiplying by 2. And big O notation doesn't care if you multiply by a constant, but it does double the time that it would take.
Thank you. I actually had the same idea of the complexity.
Cool. Any other? Okay, let's go forward. Another problem that is particularly salient in RNNs, and part of the reason why attention models are so useful, is vanishing gradients. But you should be aware of this regardless of whether, no matter which model you're using. And thinking about it very carefully is actually a really good way to design better architectures if you're going to be designing.
Sorry if we're meant to say the answer verbally to our screens door style. Yes, you should. You should. And then I wait a second and say, me too. I like vanishing gradients. What about you?
Actually a really good way to design better architectures if you're going to be designing architectures. So basically the problem with vanishing gradients is let's say we have a
One shouldn't like vanishing gradients, by the way.
Task where we're calculating a regression. We're inputting a whole bunch of tokens and then calculating a regression at the very end using a square error loss function. If we do something like this, the problem is if we have a standard RNN, when we do backprop, we'll have a big gradient, probably for the first RNN unit here. But every time, because we're running this through some sort of nonlinearity, for example, if our nonlinearity is a tan h function, the gradient of the tan h function looks a little bit like this. And here, if I am not mistaken, this peaks at 1, and everywhere else it's 0. And so because this is peaking at 1, everywhere else it's 0, let's say we have an input way over here, like minus 3 or something like that. If we have that, that basically destroys our gradient. Our gradient disappears for that particular unit. And, maybe one thing that you might say is, oh, well, if this is getting so small because this only goes up to 1, let's do 100 times tan h as our activation function.
Wouldn't that be too much?
Times tan h, and so now this goes up to 100, and now our gradients are not going to disappear. But then you have the opposite problem. You have exploding gradients where it goes up by 100 every time. It gets unmanageable and destroys your
exploding gradients. Name a band. Good name, band name.
Gradient descent and stuff. So basically, we have this problem because if you apply a function over and over again, your gradient gets smaller and smaller and smaller, bigger and bigger every time you do that. And
can't you just add a random noise somewhere? I don't know why. I'm sure someone thought of it, tested it, and didn't work. Okay.
You have the vanishing gradient or exploding gradient problem. It's not just a problem with nonlinearities, so it also happens when you do your weight matrix multiplies and other stuff like that. Basically, anytime you modify the input into a different output, it will have a gradient, and so it will either be bigger than 1 or less than 1. So I mentioned this is a problem for RNNs. It's particularly a problem for RNNs over long sequences, but it's also a problem for any other model you use. And the reason why this is important to know is if there's important information in your model, finding a way that you can get a direct path from that important information to wherever you're making a prediction often is a way to improve your model performance. And
that's the $1,000,000 question.
If there's unimportant information, if there's information that you think is likely to be unimportant, putting it farther away or making it a more indirect path so the model has to kind of work harder to use it is a good way to prevent the model from being distracted by like tons and tons of information. Some of it.
Someone give me that thing. The thing he's talking about. Preventing me being distracted. Always.
Which may be irrelevant. So it's a good thing to know about in general for model design. So how did RNNs solve this problem of the vanishing gradient? There's a method called long short-term memory.
LSTMs.
And the basic idea is to make additive connections between time steps. And so addition is the only addition, or kind of like the identity, is the only thing that does not change the gradient. It's guaranteed.
Modern transformer answer, just add residual connections. So this is an old solution, but how transformers... You mean like just use everything? That's what transformer is doing. It's like, hey, it made me think of No Face. Are transformers No Face? It eats everything? No, transformers... I guess No Face is pretty nice. Yeah.
Guaranteed to not change the gradient because the identity function is like f of x equals x. And if you take the derivative of this, it's 1. So you're guaranteed to always have a gradient of 1 according to this function. So long short-term memory makes sure that you have this additive input between time steps. And this is what...
Is the additive something like made up, or is it the one that he's talking about? Because that would be weird.
It looks like. It's not super important to understand everything that's going on here, but just to explain it very quickly, this...
My favorite thing. You don't have to understand what's happening on the screen. I'm like way ahead of you.
C here is something called the memory cell. It's passed on linearly like this. And then you have some gates. The update gate is determining whether you update this hidden state, or how much you update given this hidden state. This input gate is deciding how much of the input you take in. And then the output gate is deciding how much of the output from the cell you
That's complex, all of those decisions.
Basically push out after using the cell. So it has these 3 gates that control the information flow, and the model can learn to turn them on or off or something like that. So that's the basic idea of the LSTM. And there's lots of...
Residual connection is like you let the output from previous layer get added back. Autoregressive, I guess? Or is that different? To the output from the current layer, so the gradient can propagate better. Residual means something that's being left over. Residue, right?
Of other like variants of this, like gated recurrent units that are a little bit simpler, but the basic idea of an additive connection plus gating is something that appears a lot in many different types of architectures.
Cool.
Any questions here?
No.
Another thing I should mention that I just realized I don't have on my slides, but it's a good thing to know, is that this is also used in deep networks and multi-layer networks.
Hey, he's
And so
going back.
basically,
Okay.
LSTMs, this is time. LSTMs have this additive connection between the memory cell where you're always adding this into whatever input you get.
Mm-hmm.
And then you get an input and you add this in, you get an input. And so this makes sure you pass your gradients forward in time. There's also something called residual connections, which I think a lot
What? Give Coffee a round of applause.
of people have heard of if you've done a deep learning class or something like that. But if you haven't, they're a good thing to know. Residual connections are if you run your input through multiple layers. Like let's say you have a block here. Let's call this an RNN for now because we know about RNNs already. So RNN. So this connection here is called the residual connection, and basically it's adding an additive connection before and after layers. So this allows you to pass information from the very beginning of a network to the very end of a network through multiple layers. And it also is there to help prevent the gradient vanishing problem. So like in a way you can view LSTMs. What LSTMs are doing is preventing loss of gradient in time, and these are preventing loss of gradient as you go through like multiple layers.
Layers.
And this is super standard. This is used in
clap, clap, clap.
transformer models.
I think actually,
Llama and GPT and whatever else.
you can't see it, but YouTube allows you to react. You can't see it on the on my side. Yeah. Yes. Clap, clap, clap. Cool. Do you know that each time he says cool, it's because oh, there, I see it. Hey, oh, I can see it. Oh, yeah, we have the party one, not the so many party. Okay. Cool. He said cool, which means we're done with this section, right?
Any other questions about that?
We're good.
Okay.
Okay, so I know Keen was keen to learn about convolution, but time's up. After, and I'm guessing it's going to be a long one. Wait, what? What? It's 3 minutes. You know what? We're plowing through.
Cool. So next I'd like to go into convolution. One thing I should mention is RNNs or RNN style models are used extensively in very long sequence modeling. And we're going to talk more about like actual architectures that people use to do this, usually in combination with attention-based models, but they're used in very long sequence modeling. Convolutions tend to be used in a lot in speech and image processing.
Speech? No. Speech is all transformers now.
And the reason why they're used a lot in speech and image processing is because when we're processing language, we have like, this is wonderful.
Yes, this is wonderful. Okay.
Like, this is wonderful is 3 tokens in language. But if we look at it in speech, it's going to be like
Characters?
many frames. So
And even spaces are things, right?
kind of the semantics of language is already kind of like if you look at a single token, you already get something semantically meaningful. But in contrast, if you're looking at like speech or you're looking at pixels and images or something like that, you're not going to get something semantically meaningful. So convolution is used a lot in that case. And also you could create a convolutional model over characters as well. So what is convolution in the first place? As I mentioned before, basically you take the local window around an input and you run it through basically a model. And a good way to think about it is it's essentially a feed-forward network where you concatenate all of the surrounding vectors together and run them through a linear.
When I see it that way, I just see pixels, you know, because local pixels around it. A frame is like 525 ms chunk of sample, right? I think you can take samples however you want them. Can't be sure. Like, oh, what he was creating? I don't know. I'm not sure. The blocks. These are frames? Because I know there's a difference between how many, like how many seconds the model takes. Because like Whisper, I think max is 20 seconds. But 20-second chunks. But what you're saying is milliseconds. Speech frame, yeah, like a frame for, yeah. Should we check? Speech frame. Sure, I don't know. Rate, let's call it ASR or something, so that it gives us something that framework, not what I wanted. If I can't find it by skimming, then I can't find it and I'm out of here. I'm out of here. Sorry.
Your transform like this. So you concatenate xt minus 1, xt plus 1. Convolution can also be used in autoregressive models. And normally, like, we think of it like this. So we think that we're taking the previous one, the current one, and the next one, and making a prediction based on this. But this would be good for something like sequence labeling, but it's not good for something like language modeling, because in language modeling, we can't look at the future, right?
No.
But there's a super simple solution to this, which is you have a convolution that just looks at
The past.
basically, and predicts the next word based on the current word in the past. So here you would be predicting the word movie. This is actually essentially equivalent to the feed-forward language model that I talked about last time. So you can also think of that as a convolution, a convolutional language model. So whenever you say feed-forward or convolutional language model, they're basically the same modulo with some details about striding and stuff, which I'm going to talk about at the end of the class today. Cool. I covered convolution very briefly because it's also the least used of the three sequence modeling things in NLP nowadays. But are there any questions there, or can I just run into attention?
I don't know if that was useful, Keen.
Okay, cool. I'll go into attention next.
Yep. What? Attention is 2015? Cool. Attention is all you need, the paper. Maybe Google, like, speech framing based processing. Let's do that. There you go. 10 millisecond is here. 25. Typical window. Typical, yes. 10 to 25. Cool. Attention came before transformers. Yes. Transformers is using attention. No? I'm just saying that 2015 is the attention result. Or is that the Transformers paper, the one that I'm referring to? Ah, got it. Okay. Wasn't that 2017? don't have the energy to check. It is. Whoa, we are on time. Yes! Attention is only needed is 2017. I have my history. Right. Okay. Why am I so low? Cool. Recap. What did we learn? Let me go back to the screen. I always forget to do a recap. We looked at the slicing and dicing part of chapter 5 of the NLP course on HuggingFace, and we looked at slicing and dicing our data, creating new columns. We used the map function quite a lot, and we learned how to use Lambda in a nice way. We stopped at the map method. That's where we are. And then we went here and we looked at sequence modeling. We started with where were we? RNNs? No. This is where we stopped. 3 major types of sequence models: RNN, CNN, and attention. And then we are stopping at attention. That's where we are. Okay. And that was 2 hours of today. Oh, we learned map doesn't change the data if it's called on its own without giving the output back, without it being assigned. We did learn that, didn't we? That was my favorite part of today's lesson. Yes. I mean, how can we not say it's Dora style when we're working with the map? Okay. The map was a big character today. Alright. So, it's Thursday. Who doesn't love a Thursday? I think Thursdays might be my favorite. I mean, I understand weekdays are not the same because Friday is the first day of the weekend for me. But, so it'd be like calling everybody loves Friday because it's like the almost weekend. That's Thursday for me. So, I love Thursdays. They're blessed day. I'm not kidding. Thursdays and Mondays. I don't have to explain it. But like Friday is the most blessed. Anyway. Yes. And yeah. Okay, I don't have to go into that, but I do feel bad for the Muslims that have to work on Fridays and miss Friday prayer sometimes. Because, thank God it's Friday. It's Thursday. You should have that. TGIT. Yes, that should be the Muslim version of thank God it's Friday. Okay. That's it for today. I am awake now. I was less awake from the beginning of the stream because I woke up. Oh wow, someone followed. Hi, hello.
Corey just followed.
Thank you.
L welcomes you.
Did you realize I completed a follower goal? Daja. See, that's for the follower goal.
We reached our followers goal of 100. Thank you, everyone.
Yay! Thank you, Dajo, Corey. If you have the energy to say hi, please do. If not, no worries. Great session. Thank you, honestly. I really, really, really appreciate the fact that we're learning together because it makes it less daunting. And when I make mistakes, I don't feel like I feel like I'm in a place of people being kind and understanding even when I make mistakes. So I really appreciate that. Before we leave, what should our updated follower goal be? I'm thinking 110 so that we hit it rather, I don't know, I wouldn't say like fast, but rather manage goals. Someone give me a goal so that I goal it. I make it a goal. Okay, yeah. If anyone's curious, I'm going to share the screen where I'm looking at Twitch stuff. You wanna see it? Do you wanna see it? Ta-da! This is the behind, and there's a ad happening. We have manage goals, and then it's like based on the size we recommend follower of 110. So if I just say start new goal, it happens because it's an auto goal. Sure, why not? As a viewer, I don't like follower goals much. They're more for the streamer, I think. I bet. It's just fun, like having something to look forward to. I like the animation alerts. Yeah. It's a way of engagement. When Coffee starts streaming, we'll make sure that he will set follower goals. Not that it matters, it's just something for fun. Okay. Now we can go. So yes. Tomorrow is Friday, and we will continue with the Hugging Face part, and then later... Oh, no need to apologize. No, it's just an opinion you have, which is cool. Like, you are human. You don't have to have the same opinion as me. Thank you for stopping by, and I hope we learned something together. I sometimes, I know you guys have more experience than me, so I feel like I'm forcing you to learn things you already know. So I hope it's not the case. I hope we learned cool stuff together, and inshallah we'll do so continuously. Yeah. I guess see you tomorrow. Do let me know if there's anything, whether it's on Discord, on Twitter, whatever. Otherwise, see you next time. Thanks for all the chat and all the help, and for not catching the bug, even though, yeah, it was my bug, it wasn't yours. Okay. Yeah, have a great one. I see you and I follow you. Thank you for seeing me and following me. That's a cute statement. Cheers. Yeah, we're ending the stream right now, but we will have another one tomorrow, 2 hours earlier. So if you'd like, do come by. If not, catch us next time. And ending the stream in 5, 4, 3, 2, and 1. Goodbye. Okay.